So thanks very much to the organizers for the invitation to talk today, and thanks to everyone for all of the really engaging discussions so far. I'll be talking about lattice QCD and neutrino interactions. Much of this will appear within within a broad white paper on neutrino scattering, connecting lattice QCD, nuclear effective theories, and event generators. So compared to many applications of lattice QCD, the connection to neutrinos is relatively recent, but it's a rapidly growing area that I'd like to share some of my excitement for. So neutrino oscillations provide a fascinating window into beyond the standard model physics that we can actually measure in a laboratory. We know that neutrinos have mass, but we don't know whether it's Dirac or Majorana, what the mass ordering is, how much oscillations violate CP, and whether there are sterile neutrinos. So you'll be hearing more about what neutrinos can teach us about some of these big questions from Pedro Machado later today, as well as Alex Friedland, Muchen Chen, and Zara Tabrizi tomorrow. Suffice to say for now that the next generation of accelerator neutrino experiments, including the deep underground neutrino experiment under construction at Fermilab, aim to make unprecedentedly precise measurements of neutrino oscillations in order to better understand some of these mysteries. So where do the quarks come in? Well, the near and far detectors, of course, which are filled with atoms, in this case liquid argon, and the bulk of Dune's data will be measurements of the final states of neutrino-nucleus collisions with image-like precision that will give you events that look something like this one from microwave. So if you had a monoenergetic neutrino beam, then the ratios of numbers of observed events between the near and far detector would immediately tell you the ratio of neutrino fluxes at the two detectors, which depends on the oscillation probability and therefore can be used to measure the oscillation parameters of interest. However, accelerator neutrino experiments produce very broad neutrino fluxes with support from hundreds of MeV through several GeV, and cross-section uncertainties can be very significant. And although the effects of these uncertainties are challenging to propagate, the Dune collaboration estimates that few percent uncertainties are needed to maximize the discovery potential of Dune, and that each percent matters. So calculating these cross-sections is important for theory to deliver, but is challenging, because this broad flux covers regions where different physics processes dominate the total cross-section, from quasi-elastic scattering of neutrinos more or less off a single nucleon at low energies, resonance production at intermediate energies, and deep inelastic scattering involving quarks and gluons at high energies. There are different effective theories for efficiently describing nuclei at these different energy scales, and they have different inputs that need to be known with precision in order to achieve the few percent uncertainty goals of Dune. These inputs, in particular Nucleon form factors, pion production amplitudes, two-body currents, and DIS structure functions, are where lattice QCD can help neutrino-nucleus scattering cross-section predictions. So Lattice isn't going to do this alone. It's going to be part of a pipeline involving nuclear effective theories and neutrino event generators in order to actually impact phenomenology and experiments. And this is in large part because of the complementarity between what Lattice can offer for these sort of inputs and what we can get experimentally that I think is worth emphasizing here for a moment. So lattice calculations, including baryons, are much noisier than those containing only mesons, and the noise grows exponentially as you increase the baryon number. We also can't do lattice calculations in real time because of the sign problem, so real-time scattering of a nucleus is about as hard as it gets, especially when you have multi-hadron states around. The other traditional challenge for lattice has been getting down towards physically light quark masses, though with modern algorithms and computing resources, this is hard but achievable. So what lattice can offer is ease of switching between vector and axial currents with no changes in difficulty or systematics, flavor decompositions and looking at isovector versus isoscalar quantities without much change in precision, or with the isovector even coming out a little nicer on the lattice side. And pions are relatively straightforward. And this points to a synergy where lattice can try and provide constraints on things that we don't know very well from experiments about the nucleon and few nucleon systems. So one slide on lattice QCD technology, we're not putting a neutrino or even a W boson on the lattice here. We're starting by factorizing the matrix elements into leptonic and hadronic parts. And all we were trying to calculate are the matrix elements of hadronic currents, so the vector and axial currents that you need for electroweak processes. And generic matrix elements of observables can be calculated by first integrating out the quarks analytically. So you just need propagators that you have to invert very, very, very large, but matrices for. And then the gluon fields are Monte Carlo sampled with some probability proportional to e to the minus action, which allows us to access Euclidean correlation functions. And in particular, the nucleon is the easiest lattice system of relevance here. And the relevance is really through the impulse approximation and its generalizations. That at scales where we resolve an individual nucleon instead of the coherent scattering off the whole nucleus, you can approximate the Neutrino-nucleus cross-section as a sum of form factors involving the individual nucleons times nuclear spectral functions showing how they're distributed throughout the nucleus. And so these nucleon vector and axial form factors are key inputs to nuclear effective theories and models. The form factors are just defined through decompositions of matrix elements. For instance, the axial current has an axial form factor and an induced pseudo-scalar form factor, much like the electric and magnetic form factors of the vector current. In fact, these electromagnetic analogs are very precisely measured with electron scattering, which provides important validation for lattice QCD and for lots of other aspects of these neutrino-nucleus cross-section calculations. And of course, the nice thing is that we're not limited by the impulse approximation here. This is the first step in an expansion of including multi-nucleon effects. So lattice calculations of the vector form factors are getting quite mature and have now been performed using physical quark masses at several different values of the lattice spacing that enable continuum extrapolations. And as you can see from these curves, there's very nice agreement between modern state-of-the-art lattice calculations. This is by the nuclear matrix element collaboration, the Los Alamos group and collaborators. And you can see great agreement between the lattice results and phenomenological parameterization of experimental data. And this agreement is really only after doing everything carefully, getting physical masses, accounting for excited state effects in particular. And the same group has noticed that a careful treatment of nucleon-pion excited state effects is essential to reproduce consequences of the axial Ward identity, assuming you're in the ground state, that provide a nice test for these sort of excited state issues, and have found that careful analysis is able to get consistency with these relations, but a naive analysis can have order 10% deviations. So that brings me to the status of axial form factor results. It's exciting to say that there's 7 lattice calculations shown on this nice review plot by Aaron Meyer and collaborators that have results with physical quark masses. The 2 with bands here include full continuum extrapolations and some estimate on those systematic uncertainties. Now you'll notice there's some deviations between the lattice results and phenomenological extractions from deuterium bubble chambers, and these could still be arising from challenging lattice systematics, these excited state effects in particular I was just talking about, or the lattice spacing extrapolations, which still need to be performed more comprehensively. But it's also interesting at this level to look at whether there could be underestimated systematic uncertainties in the phenomenological extractions of the axial form factor, since in principle the lattice results here are starting to include all of the pieces of QCD that we expect to need here. So it'll be interesting to see how this evolves on both sides. Okay, and with that, I'll move on from form factors, because of course a nucleus is not just a collection of nucleons, and it's been known for quite some time that there's modifications of the axial response of a nucleon within a nucleus. So the modern view of this within effective theory is that you need to include multi-nucleon correlations in your nuclear state and multi-nucleon currents in order to reproduce experimental results for things like beta decay rates of medium mass nuclei. And it's also known that these two-body current effects are important in neutrino-nucleus scattering at the precision that we're aspiring for here. So there have been exploratory calculations to try and get at these 2-nucleon currents from lattice QCD using exploratory ensembles with very heavy quark masses corresponding to 800 MeV pion masses, where the signal to noise problem is much less severe. And with these calculations, we're able to see sort of shell model-like structure begin to emerge even at unphysically heavy quark masses, and we're able to start taking crude extrapolations towards the physical point now for the Gamow-Teller matrix element governing the triton beta decay rate with 2 quark masses that still have systematic uncertainties to be quantified, but find encouraging agreement with experiment for the triton beta decay rate and for the correlated 2 nucleon coupling L1A within pionless EFT that this was matched to by Detmel and Shanahan. Okay, excited state effects like these pion nucleon ones show up in force in the 2 nucleon sector as well, where you have small gaps to unbound 2 nucleon excited states. And there's been a lot of progress in recent years to develop better algorithms and harness better computing to build variational calculations that can actually take a set of operators and use QCD imaginary time evolution to filter out the best approximation to the ground state and some tower of low-lying excited states that have good overlap with your operators in a calculation. So for algorithmic reasons, all of the matrix element calculations I've talked about so far for 2 nucleon systems on the last slide use a limited set of these interpolating operators, and recent studies have shown that excited state effects can be larger than previously expected there, and this is something that needs to be controlled. But with these sort of variational methods, it's also possible to harness the power of Lattice QCD for the resonance region. And you can both remove explicitly the nucleon-pion excited state contamination from elastic form factor calculations, and also by studying both the isospin 1/2 and 3/2 sectors, look at nucleon to delta production amplitudes. So there have been impressive steps made in this direction by a couple of groups to perform these variational studies of nucleon-pion and delta systems. The finite volume energy spectra in a really tour de force calculation by Sylvie et al. Have been mapped through generalizations of Lucia's quantization condition in order to determine the P wave and pi phase shifts. And you can clearly see the emergence of the delta resonance here, even at quark masses light enough for the delta to be a resonance. I'll also highlight the Regensburg group has made some impressive first steps towards these off-diagonal bits here to do the transition form factor calculations that you need for electroweak delta production. Okay, and in the last few moments, I'll just mention that as you go up to higher energies, it becomes impractical to try and map out every state exclusively, but there's alternative methods involving the hadron tensor that have been developed and are being tested out, in particular by the KITP collaboration, as well as Hashimoto and collaborators, to try and get at inclusive scattering cross-sections even above these inelastic thresholds. Finally, you'll hear much more next talk from Hui-Wen Lin about how Lattice QCD can shed light on deep inelastic scattering by calculating quark and gluon PDFs and other generalized structure functions. In particular, I'll just highlight the things that are important for neutrino DIS. So the axial current and charge current flavor structures that show up can be calculated by Lattice QCD similarly to the unpolarized ones that can be constrained and validated experimentally. And that there's even first steps towards learning about multi-nucleon effects on these PDFs from Lattice QCD that could again, hint at neutrino DIS specific modifications that are otherwise hard to constrain. So I have no time left, but I would be remiss to not mention that there is other neutrino physics that you can't get at easily with accelerator neutrinos, in particular searches for Lepton-number violation through neutrinoless double beta decay. And there's been really a explosion of theoretical interest in sort of nailing down the nuclear effective theory of these matrix elements, discovering that there's a short distance contact operator needed for normalizability and starting to constrain it and add it to many body calculations. And Lattice QCD is also a growing part of this effort. So there have been calculations of pion analogs of these double beta decay matrix elements both involving short-distance new physics operators, as well as the long-distance Majorana neutrino exchange mechanism. And there have been calculations of 2 nucleon matrix elements for 2 neutrino double beta decay, which are, of course, a stepping stone to doing 2 nucleon neutrino list double beta decay matrix elements that could help constrain these contact operators that I just referred to. And
Michael, your time is up. Can you?
A major effort of both algorithms and formalism. So with that, I will finish up and take questions. Thank you very much.
Thank you very much. Thanks for this nice talk. And we will start with questions from the room. Lance, can you say your name before you start?
Sorry, Lance Dixon. Thanks for a very nice talk. Can you say a little bit more about inclusive methods and what are the restrictions on them?
Yeah, good. So I brushed over this. The idea is that you really calculate the 4-point current correlation function in, say, the nucleon state that you map to the optical theorem here. And the tricky part is that what you calculate is the Euclidean current correlation function, and what you want is the Minkowski version. So there's an inverse Laplace transform that you need to go from one to the other, and this is really the primary novel challenge in these calculations. And so there have been different methods ranging from maximum entropy to Backus-Gilbert and other things that have started to be explored here for this step of the calculation.
Do you know if people have thought about putting in measurements so it's not totally inclusive, but is weighted in some way too?
So the closest approach here is a really nice paper by John Balava and Max Hansen that showed that you can get particular final states through generalizations of this formalism, let's say. But this has been proposed, but has not yet really been implemented yet. So people are thinking about it, but it's...
Yeah. Thanks a lot.
More questions from the room before we move to Zoom? Nathaniel, do we have questions on the Zoom side? Okay, then I guess the talk was pretty clear. So thank you very much, Michael, again. Thanks.
Thanks.